Okay, I'm just going to talk through the solution to question 1, page 140 in the study guide, also called activity 9b. So question 1 talks about a diagram of a wheel, and it's attached to a mass which is allowed to fall. Now, of course, as soon as you release that mass, the string will attempt to fall with the mass, but the rotational inertia of the large wheel will reject, or resist is the right word, resist the acceleration of that string, and that's due to the rotational inertia of the wheel. It really depends how large that rotational inertia is as to how much tension is generated in the string. That tension force will be, of course, an upward resultant force, sort of affect the resultant force of the falling mass. So that's the situation, a common situation for these types of questions. I've started by listing out the information given. Here the mass is 0.50 kgs, the radius is 0.10 meters, and the acceleration given was 2.0 meters per second squared. It's a good strategy to always do this for all such questions. It just clarifies in your mind what kind of equation is likely to be asked for and exactly what information you have, and the units, of course. It draws attention to the units. The first question then is to find the unbalanced force on the mass. I've written that as F net, and of course the equation for the unbalanced force is M times A, mass times acceleration. So we have both of those figures given, 0.5 and times 2, that gives us 1.0 newtons. And that's accurate to two significant figures. Part B, they're asking for the tension force, and to show that it is 3.9 newtons. To understand this, we first of all need to calculate the weight force. So that's the other force, of course, acting in this case, the weight force of the mass, Fw. Mass times gravity, that's of course going to be 0.5 times 9.81, 4.905. That's significant to two figures, so 4.9. In this case, both the net force, or the unbalanced force, and the weight force are downwards, while the tension is upwards. So we can write an equation like this. The net force is going to be the weight force, take away the tension force in the string. Rearranging and solving for t then, we can prove that it's going to be 3.9 just by subtracting the net force away from the weight force, as follows. Part C, they're asking you to calculate the torque acting on the wheel. So now that we know the tension force is indeed 3.9, that tension force is the thing acting perpendicular to the rotation of the wheel, of course. That's going to be multiplied by the perpendicular distance to the centre, which is the radius, and that's 3.9 times 0.1 gives us 0.39 Newton meters. How do you know not to use, say, the weight force? Well, the weight force is not acting on the rim of the wheel. You have to always go to the rim of the wheel and say, okay, what force is acting there? It's generally always a tension force. Part D, calculate the angular acceleration of the wheel. That, of course, is related to the linear acceleration of the mass divided by the radius. So we plug those two numbers in and we get 20 radians per second. In Part E, calculate the rotational inertia of the wheel. Now that we have both the torque from Part C and the angular acceleration from Part D, we can use the relationship between those two, giving us the rotational inertia I as torque divided by angular acceleration alpha. And that comes out to be 0.020 kilogram meters squared to two significant figures. Okay, number 2, just to carry on, very similar question. This time it's a It's a rotating turntable with another pulley, just to complicate things slightly. First question is asking, describe and explain the motion of the rotating turntable. Well, it must be moving with constant angular acceleration, as shown by the linear graph, showing a constant rate of increase of angular velocity. So if you look at the graph, it's a straight line, and that means the angular velocity omega is increasing at a steady rate through time. That, of course, translates to an angular acceleration. Question 2, what is the value of the angular acceleration of the rotating turntable? That is found from the gradient value of that graph. So it's the change of angular velocity omega over time, which is going to be, there's a good point on the graph, at 8 and 20. After 20 seconds you can see it's on 8 radians per second. So dividing that gives you 0.40 radians per second squared for the angular acceleration. Number 3, from the graph, find the angular displacement. That's equivalent to the area under the graph, in this case, which is going to be half base times height, half 20 times 8, it's 80 radians. You could also find it using the kinematic equation theta equals omega it plus a half alpha t squared, which will give you the same answer. Radius, okay, what is this one about? They're asking us which radius we should use, given the two pulleys. Since well, it's pretty obvious, I suppose, which one to use, but why? The radius R should be used since the linear acceleration of the string and falling mass depend upon the angular acceleration of the pulley of radius R, which is attached to the turntable. And that, of course, you could carry on to say that turntable altogether will have a rotational inertia I, just to make sure of your answer, that could be something to add in there, which will determine the size of the angular acceleration that is possible, and hence the linear acceleration of the mass. Question B gives you another graph, and they ask you, they've plotted torque against angular acceleration alpha, and they're asking what physical quantity does the slope of the graph of the torque against angular acceleration represent. Of course, it's the rotational inertia I. That's the ratio of torque to angular acceleration, and the units are kilogram meter squared. If you didn't know that, you could work out that from the gradient calculation, dividing the units of torque by the units of angular acceleration. 1 Newton is kilogram meter per second squared, of course. So putting that in on the top line gives you kilograms meters squared per second squared for the torque, divided by radians per second squared, and since a radian is dimensionless, you just ignore that. The second per second squareds cancel out, leaving you with the kilograms meters squared. Unit.